Alkenes, compounds with double bonds, undergo electrophilic addition, and they do so with a number of reagents. Typically though, in many times, or in many examples of reactions, we carry out these kind of electrophilic additions to produce things like alcohols. So what we have here is hydroboration and oxidation. This is actually a two-step mechanism because there are two different reactions that are actually taking place. The first one is hydroboration and the second is the oxidation step with peroxide. So we'll do this, okay, and treat this as two separate reactions. So we begin, of course, with our alkene, and we see that it's a substituted alkene because, of course, there's a methyl group. Now, if there was no methyl group, then we would say it's unsubstituted. But we have a methyl group. And this substitution here is actually very important because it will actually influence the type of product that is formed. Now, when you look at it, what I want to do is I want to add this borane either to this one or to this one, okay? So I'm trying to produce the product of hydroboration. Now, as you can see, I have 1, 2, okay? 1, 2. Another issue is, notice that I have 2 double bonds. So am I going to add to both? No. Actually, what's going to happen is that the more favored or more substituted, okay, region is where the reaction takes place. So the reaction won't take place over here. The reaction takes place over here because we have a methyl substituent. Okay, so that's the first thing we've decided. So now I have 1, 2 carbons that are involved in the double bond. The next question I have to ask myself is, will I add to this carbon? For instance, will I add borane here? Or will I add it down here? Okay, so hydroboration, okay, actually produces something known as the anti-Markovnikov product. What do I mean? So let's take a general double bond. If I have a double bond, okay, and I have only hydrogen atoms attached, then when I go through hydroboration, it doesn't matter where I place borane, right? I can do it on the left or I can do it on the right. Doesn't matter, right? Because it's symmetrical. But what if I have a methyl group? Then it's a little bit different because now I can't just add it to any carbon. Which one receives it? Now the Markovnikov rule says, listen, when you're doing this type of thing, okay, that like will go to like, right? In other words, you're going to add a hydrogen atom, okay, to the carbon that has more hydrogen atoms. This is the Markovnikov product. So it actually break this bond, and let's do this over here, by creating the following 2 additions. I would add a hydrogen atom here, and then I would add my borane here. Okay, this is the Markovnikov product. It says like goes with like. And so, another way to look at this, C1 has 2 hydrogen atoms, C2 only has 1. So the hydrogen atom will go where there are more of them. This is Markovnikov's rule. But hydroboration, followed by oxidation, actually produces the anti-Markovnikov product. So you get the opposite effect. So this is Markovnikov, so we'll put M, I'll just write Mark for Markovnikov. But what we really see is this. We see the hydroboration process yield a situation, actually let's do it in another color, where the borane actually goes to the carbon that has more hydrogens, okay? And then the hydrogen goes over here. So that's the opposite effect. This is called the anti-Markovnikov product, okay? So hydroboration produces, and I'll put it up here, the anti-Markovnikov, okay? The anti-Markovnikov product. So we can now figure out what it is for our reaction. So let's see. We're going to open up this bond. We have a methyl group. If you have a carbon attached here, this carbon versus this one, this carbon is attached to 1, 2, 3 carbons. It's tertiary. So it doesn't have any hydrogen atoms at all. This carbon is attached to 1, 2, 3. It has a single hydrogen atom. So now, actually let's put this in brown so we don't confuse ourselves. It has a single hydrogen atom. So based on what we've learned with the anti-Markovnikov product, we're going to have the opposite of what we expect. Markovnikov says when we do this hydroboration, the hydrogen should come to this side and the borane should go to that side, right? Anti-Markovnikov. So what do we see? If that's the case, we're going to have our H here, but we're going to add our borane here. And then we're going to add our hydrogen here. Okay, so that's the anti-Markovnikov product. The anti-Markovnikov product. Now, the next step is to figure out what we do in terms of oxidation. So, this actually gets easy. In the oxidation step, we have a CH3 here, we have a borane, sorry, and we have hydrogen peroxide. And so now all we have to do is to replace this, because the peroxide is going to come here and displace it, and you're going to have the peroxide here. Okay? So that's the anti-Markovnikov product. Markovnikov's rule says there are hydrogens here, so hydrogen should come here, and borane would go here. But this is the anti-Markovnikov product. So instead of hydrogen coming where there's more hydrogen, the hydrogen goes up top to the methyl group, and the borane comes down here. That's in the first step. And then in the oxidation step, we see that we replace the borane group with the hydrogen peroxide. So the summation, or the bottom line, is simply this. Hydroboration oxidation yields the anti-Markovnikov product.